In this tutorial, I'm going to show you how to run Moose on Windows. The first thing we're going to do is make sure that we can get Windows Subsystem for Linux up on our computer. So I'm going to come down here to the search bar. I'm going to open up Windows PowerShell. And I'm going to type WSL -- install. It's downloading Ubuntu, which is awesome. Ubuntu is just, they call it a flavor or a distribution of Linux. So that's what the WSL is going to use to run Linux. WSL is just a virtual machine. And it was successfully installed. Now it's launching. We just have to wait for it. It's doing some backend stuff. I want my Linux username to be FBSmith, so I'm going to set it as that. Press enter. It's going to ask me for a password, so I'm going to now enter my password. Notice that it doesn't look like I typed anything, but I did. So don't be fooled by that. If you start typing and want to undo it, you can do backspaces. But I typed in the password that I want, and I'm going to press enter. It's going to ask me to retype it to confirm it. So I think this goes without saying, but make sure you remember your password, write it down somewhere safe, because you will need it for stuff. So that worked well. I now have a Linux terminal. I'm actually going to exit the PowerShell. I'm going to close that out. Yeah, welcome to WSL. I'm going to open WSL properly. So I'll just search for WSL and open that. And here I come. I'm going to CD. So now I'm going to teach you guys a few simple Linux commands. The first thing that we're going to do is ls. ls lists everything in the directory. There's nothing in here so far. I can also CD. When I CD and just press enter, that'll put me into whatever the home directory is, whatever the root is. So right now, that's a little squiggle. I can also do pwd, and that'll print my current working directory. In Linux, that will usually be /home/ whatever your username is. So the first thing I'm going to do here in Linux is I'm going to run some updates. So I'm going to do that by typing sudo apt update. Now it's going to ask me for my password, and because I remember that, I'm going to put it in. I'm going to press enter, and it's going to go and it's look for all the updates. Now it did just install it, but that doesn't necessarily mean it's the most up to date, so we just want to make sure that we can update it. I'm going to go ahead and type sudo apt upgrade, and it's going to ask me if we can do that. I'm going to say yes, and sweet. I'm going to press clear. You may see me do that a few times. Whenever you do clear, it just clears the screen. So it's very convenient. Now we are ready to go and start with our Conda installation. In order to do that, I'm going to pop open my favorite web browser. I'm going to search inl moose installing moose. So I'm going to come to the installing moose page. Because I already have WSL and I'm already in a Linux terminal, I'm going to click on the Linux and Mac OS. The first thing I'm going to need to do is to get Conda on my system. So I'm going to copy this command right here. What this command is going to do, I'm going to paste it in here. Make sure I get the 8 on the end. What that's going to do is it's going to go out to the website that it has there and install a file. So now if I ls, I can see that .sh file has been downloaded. Now I'm going to copy this second command right here. This is bash. Oops. And what that's going to do is it's going to execute that .sh file, and it's going to put everything that it needs to in a file called MiniForge. So it's going to do that. Perfect, it's finished. Now if I ls, I can see right here MiniForge is in blue. Blue means that it is a directory. A directory is the Linux word for file. And the .sh script is right here in white. Normal files are just in white in Linux. So I don't need that anymore. So the way that you can delete a file is going to be by pressing RM and then whatever the file name is. I don't have to type in the whole file name. If I just start it and then I tab, it'll autocomplete whatever I have. So I'm going to delete that, and now I only have MiniForge in my system. Now I'm going to clear the screen. So I have Conda downloaded. Now I need to make sure to activate it. The first thing I need to do is add it to my path variable, so that way when I run a Conda command, the computer knows what to do. So I'm going to export path. I'm going to update my path variable. That's where the system goes to look for things. I'm going to export home. That's this current directory, MiniForge/bin. I'm going to prepend that to the already existing path variable. Bin is just short for binary files. So now that that's in the path, I can say conda init --all and initialize conda. In order for those changes to take effect, I do have to close it. So I'm going to type in exit and close the terminal. I'm going to come back and I'm going to reopen WSL. And if you notice now, I have base in parentheses before my username and the computer. That base means that I'm in the base conda environment. So I can type in conda -- version and it'll show me which version of conda I'm on. So that's very good. Just like with Ubuntu, we want to update everything. So we're here now in our installing Moose instructions. I'm going to do conda update -- all. It's going to go out to the web and see what needs to be updated. And there's just a couple things. I'm going to say yes, that's fine. Sweet. So now we have the most updated conda environment possible. What I'm going to do now is I'm going to add INL's conda public conda repository. So I'm going to do conda config -- channels https / conda. Actually, this is probably a good one to just copy and paste. So I'm going to do that. I'm going to copy that and paste it here. This is going to tell Conda that I can go out to that website to go look for packages, which is good because that's what Moose depends on. So now that I've done that, I'm going to come down here. By the way, this notice about sudo. This is important when you start to go into Linux. Sudo is short for super user do. If you think about Windows, whenever you want to download something or run an executable program, anything that ends in .exe, there will be a pop-up that asks if you want to do that, or there will be changes made on the device or something like that, and then you can run that as an admin. Sudo is Linux's version of that. So for example, earlier when we did sudo apt update, I had to do that as the super user or admin user because we wanted to make sure that whoever's adding files and packages to the computer does the right thing. You'll notice if I just do apt update, it gives me errors and it says I can't do that. Right? You'll see right here at the bottom it says permission denied, permission denied. So you want to make sure you know how to use sudo, but you only use it for the things that you need to. And conda stuff doesn't need sudo. So now I'm going to install Moose. So I'm going to start by creating a Moose Conda environment. I'm going to do that by typing in conda create -n moose dev equals 2026.02.10 equals mpitch. This is going to tell Conda that I want to create a new environment. The name of the environment is Moose, and I want to install the Moose dev package, specifically the February 10th, 2026 update. And so it's going to go out to those channels. It's going to look for that, and it will download it. All right, it's telling me all these things that it wants to download. I do need all those things, so I'm going to press Y and press enter. And it's going to give me this nice little dashboard, or whatever you will, on the download progress. It's kind of fun to see. You'll notice as a quick little fun note, we are currently, the biggest file here is libmesh. We want to be able to mesh stuff, so that's important. We're also in Python, we're on version 3.14. So we are indeed on version pi of Python. I think that's funny. There's just some small stuff it needs to download now that we can't see. All right, and it's close to being done. It's going to talk about CUDA support. You don't need CUDA support unless you have a GPU. Someday Moose will leverage GPUs more, but it currently doesn't. And for most of the stuff that we're going to be doing, we don't really need a GPU for that. All right, so now we have created the Conda, the Moose environment in Conda. We're gonna activate it, and we do that by saying conda activate Moose. Now you'll notice that I have Moose here in parentheses. If I want to deactivate it, then I can just say conda deactivate, and you'll see that we go back to base. But I want it to be activated, so I'm going to say conda activate Moose. Now we have Moose. Clear the screen. All right, we're on a roll now. Okay, next thing we're going to do, we're going to, now that we're in the base directory, I want to make a projects directory. In Linux, the way you make a directory is with the command make dir, mkdir. I'm going to name that projects. Now I will see that in my, when I list what's in my home, I see Miniforge and projects. I'm going to cd, cd stands for change directory. I'm going to change into projects, and I'm in projects. Now I'm going to do ls, it's completely blank. Now what I want to do is I want to clone Moose. Cloning is the computer science version of copying. So in order to do that, I'm going to use a program called Git, which is really nice and convenient. It's a little complicated, but I'm going to use Git. I'm going to say git clone https:// github idaho lab/moose.get. I'm going to press enter. It's going to go out to that URL on GitHub and clone the entire Moose repository into the projects directory. It is quite a large project. A lot of people have been working on it, and so it will take a little bit. All right. So now I can ls, I can see that I have Moose in my projects directory now. I can cd and if I just start it, I can press tab and auto-complete it. You'll notice that it is very, very nice. Now I ls, I can see a whole bunch of stuff in here, some directories in blue, some files in white, and an executable configure in green here. I want to now go ahead and do a git checkout master. Perfect. Now I can confirm which branch, and so master is just a branch. That means that that's a way that Git organizes how you're developing code. So we want to be on the master branch. I can double check that I'm indeed on the master branch by typing git branch. And it'll show me that I am on the master branch. Next branch is also available to me, but that's more for developers. We want to stay on master branch. Now this is where we're going to stray from the installing Moose instructions. Installing Moose instructions is going to tell you to go to the test directory and to run tests. I can show you how to do that real quick. I'm going to clear, so I'm going to go cd, the weird little squiggle, projects, Moose, test. You'll notice that I used tab a couple times there. I'm going to do ls. I'm going to say make-j6. What make does, I'll go ahead and tell you while this is working. Code in C or C++ is, I guess back up. C and C++ are what's known as a compiled language. So you write the source code, and then you have to compile it in order to actually run it. So the make command is the instructions for the computer to compile the code. The J flag, anything that has a dash and then a letter in Linux is known as a flag. Anything with a J, in this instance, the J flag is for the number of processors that you want to use, and I told it I want to use 6. So you'll see that's going to take a while. So I'm going to just cancel that process. The way I'm going to do that is just by pressing Control-C, and you'll notice that it stopped. I'll go ahead and clear the screen. I don't want to be, okay, so now I want to actually compile the code itself instead of running a test. So I want to get out of the test directory. I'm going to do that by using our good old friend CD, and I'm going to do the double dots. The double dots will move us up one directory level. So I do CD double dot, I move from projects Moose test to project Moose. I'm going to ls. The directory that I do want to be in is modules. I'm going to cd into modules. This is where we get all the different physics. So you see that there's chemical reactions and electromagnetics, fluid properties, phase field, paradynamics, Navier-Stokes, solid properties, solid mechanics. These are all different physics that have been implemented in Moose. I want to go into the combined one, so that way I get all the physics all in one. Again, I'm going to clear. And once I'm here in the combined directory, I'm going to again run our nice little command make. Now, I'll go ahead and show you something So I'm going to run make. I have my j-j. I'm going to run 6. I happen to know that my computer has 8 processors, but I'm only going to use 6 of them. And I press that, and this is going to take quite a while to compile all of Moose. Like I said, it's quite a large project. Fortunately, I have a pretty good computer, and so it's going relatively fast. You'll notice, if you notice that this make dash J, whatever number that you use for your computer, if you notice that runs into an error where it says that a file wasn't created, then what you need to do, I'm going to pretend like that happened to me. I'm going to exit the program. I'm going to pretend that it said that a file wasn't found properly. What that means is you use too many processors, and one process requested a file that should have been made by another process before it actually got made. So what you need to do in that case, it goes and it doesn't complete all the way. You need to run a command. I'm going to clear the screen. You need to run a command called make clobber all. Because what happens is we have a bunch of source code that gets compiled into small little object files that are binary, so they're computer readable but not human readable. Once they're in binary, then all the different object files will get compiled into different executables until you have just one big executable. So if the object file is not there, it's not going to see it, it's going to panic, and it's going to make your whole program crash. So the way to do that is to clobber all. What that does is it goes into every single different directory that it puts these files into and deletes all that. So as you can see, it's going to clobber in Moose framework and enter the directory framework, clobber it in there. It's going to remove a couple directories, remove a few files, and it's going to leave that. And it's going to go through that for each and every single one of the files that the directories that it built in. If you run into the case where running make -j6 or 4 or 8 or 32 or whatever number you choose, if you run into a situation where that breaks your computer, it requests a file that doesn't exist, then you will need to run just make with no J flag. That's going to use only one processor. You're not going to run into that case. If you do that, it will take a very long time to compile. So if that happens to you, start, plug in your computer, tell it to make after running make clobber, and go to the gym or go work out for a while, because it's going to take quite a while to make it. So fortunately, I think my computer can handle it. I'm going to do run make -j6, but now you guys know what to do if that doesn't work. If you notice that it crashes and it doesn't, it's not because there was a file that wasn't there, then you may not have enough memory to do that. I was working on my old laptop trying to do this earlier today, and it only has 8 gigabytes of memory. And so after running on Windows and then doing a virtual machine with WSL, it just didn't have enough memory, and so it crashed. There's some ways around that. You can ask Dr. Zhang or me if you run into that, or ChatGPT, or your large language model of choice. But you'll notice now I'm running make j6 and it's compiling. Even though I'm using 6 processes speeds it up considerably, but it's still going to take quite a while. So if you are watching this, you can just skip forward in the video until it is done compiling. Welcome back. So that took a long time. I'm going to talk about kind of what I did in order to get here, because this is the output screen, and this line right here at the very bottom where it says linking executable combined-opt, that means that I had success. So I'm going to go ahead and press ls. Now you can see what's in here. By default, we have combined opt in green. Remember, green is executable. An executable means that I can do a / combined opt, and it will be a program that will run. In this case, I didn't give it the input that I wanted, but it ran. So I had combined opt. I'm going to kind of review some of the steps that I took. I started by trying to say make J6, and that was going until it terminated the build request and stopped it. So that didn't work. So I did make clobberall to clean up the build space, and that made my instance of WSL crash. And so I kept going in a couple times and doing make clobberall. What I ended up needing to do was to make a config file, actually. So I'm going to show you guys how to do this. If you're having issues with WSL crashing, go ahead and do this. So I already kind of did this, but the way that you're going to do this is you're going to go to the search bar, you're going to come up to Notepad, we're going to open up Notepad. You're going to make a new file, and you're going to put this inside of it. Now, the first thing we have in brackets here is WSL2. That means I want to set settings for WSL2. Here's the memory. Memory I set to 8 gigabytes. My computer has 16 gigabytes of memory. It has 13 some odd available for it, but with the virtual window of WSL running and to have a safety buffer, I limited the amount of memory that WSL could use to only 8 gigabytes. I limited the number of processors that WSL could use to 6 because I have 8, but I wanted to kind of give it a limit. And here is the critical part that will probably save you. So what happened here? What happens is usually when you're running WSL and it crashes, that's usually because WSL did not have enough memory in order to do what it wanted to. And so it just freaks out and crashes. Kind of like a deer with, as you're driving down the highway that sees some headlights, it just kind of freezes and crashes. So what you can do is you can use what's called swap space. So what happens is WSL will be filling up memory. It gets close to its 8 gigabyte limit up here. And what it can do is it can use some swap space. It will take some of the memory from your RAM. It takes some data from RAM, and it will go to a location on your hard drive, right to it there, and free up some of the memory in RAM. And then when it needs it, it'll go back to the hard disk, to the drive, and will extract it and take it back. So I'm telling it that it can use 32 gigabytes of hard drive space. That's probably excessive, but I don't want it to crash. So I gave it 32 gigabytes of hard drive space. And I told it where it was okay to, as far as a file location, to put that hard drive space. You'll notice I have my C, that's your classic Windows root. And you have users, Flet C, because that's my name is Fletcher. So just cut off the HER at the end. That's my username. And this is the file, wsl-swap.vhdx is the file that I gave it to use. And critically, I put all this in a notebook file, went File, Save As, and I saved this file in my C, users, Flet C. I put it all the way down here. So you can see Here's WSL config, and there's WSL swap. I name it .wsl config, no spaces, and the default when you save it is going to be text documents. You do not want that. You want to switch it to all files and name it .wsl config, exactly that and only that. That's right here. You can see that I made it. It made a hard disk image file. So that's basically where the hard drive goes. So once I did that, I opened up WSL again and I ran only make. I think I did make clobber all at first to make sure that everything was cleared up. And then once everything was, I ran make and I went to bed and it was successful. I know it was successful because we have combined OPT. All right, so at this point, we've finally gotten to where we have a executable file, and that's awesome. So what we're gonna do, when I'm working on my project, I kind of like to have its own little space outside of Moose. So I'm gonna come back here, I'm gonna CD, just back to root, I'm gonna CD into projects, and I'm gonna list what's in there. I have a Moose directory. I'm gonna make a new directory in here called my project. Right, name it whatever you want. I'm naming my project. Right, and so I have nothing in here. So I'm going to make a copy of the executable. I'm going to do that by saying copy. I'm going to do the tilde so that way I can say that I'm referencing home. Just like right here. And I know that my executable is here in projects, Moose, modules combined. So I'm going to copy it from projects, Moose, modules combined. And I know it's combined -opt. I'm going to copy it from there to here. In Linux, whenever you're referring to the current directory, wherever you are, that is a dot. So what I'm saying is I want to copy my combined OPT from this location into this current directory. I do that, I ls, and I see that it's right there. So now I can run Moose, but what's the point of running Moose if I don't have an input file? So let's go ahead and go back. I'm going to CD into project Moose modules. And I'm going to go into one of these modules and find an example file. So let me go ahead and CD into solid mechanics, ls, and here I have, very convenient right here, examples. So let's go ahead and CD into examples. And let's list what's in there. There's a bridge, coal mining, a piston, and wave propagation, a few other things. The bridge sounds cool, so I'll go ahead and CD into bridge, ls. Okay, so now I have a bridge.e, bridge.i, bridge large strain, fake bridge.e, fake bridge.jou, and tests. I don't know what any of these things are, so I'm going to go ahead and view these files from the terminal. And now in WSL, you don't have a graphical user interface. It's only the terminal. So you're not going to be able to open up Word or Notepad or anything like that. Fortunately, we have a few text editors built into the terminal. I'm going to show you probably the most user-friendly one. It's called Nano. So in order to open that up, I'm going to type nano and the file I want to open up. I'm going to open up bridge. Bridge. And you'll notice I tabbed and it didn't completely autocomplete it because there's a couple different bridge things that could be. So I'm going to look out. I happen to know that I want the bridge.i file in Moose. any of your input files are by convention a .i. So I'm going to open up bridge.i. I can see that this is a bridge linear elasticity example, and here is my moose file. I'm not going to go into what all is here because Dr. Zhang's going to do that, and I'm sure there's plenty of other tutorials that you can see. I just know that with this one, I just wanted to get an example for you guys. So we're gonna have, this is gonna be a steady solve type, so that's kind of nice. So I like this file. What I'm gonna do, if I want to edit this, then I can just simply edit that. I can press enter and type, I am editing this example. Yay. Now, in order to save my edits, I have all these commands down here that tell me a bunch of things that I can do. I want to write out. In Linux, instead of save, they kind of talk about write. You'll notice that the Linux people like to have different words, different names for things. That's just the way that they roll. So I want to write out, so I'm going to press Control O. It's going to ask me what I want the name of the file to be. I want this to be Bridge Fletcher, so I'm going to go ahead and change that. I'll press enter. Save file under a different name, yes, because I want to keep the original example to what it was, and I edited the example. So now that I've saved it, I want Control X, and I'll exit it. So I can ls, and I've now used nano to create a new file and edit a text file, bridge_Fletcher. So now what I'm going to do, I'm going to copy. I'm not going to copy. We've used copy a few times. I'm going to show you the move. Move in Linux is MV. I'm going to tell it which file I want to move. In this case, that's Bridge Fletcher. And I want to move that into my project. So I'm going to do the curly, kind of little squiggle line. I'm going to move that to projects, my project. Sweet. Now let's go ahead and CD there. I'm going to CD into squiggle projects, my project. Now I do ls, and I see that bridge_Fletcher is there as an input, and I have combined OPT. Now I am ready to run Moose. As a reminder, I need to have my Moose conda environment active. I have my executable right here, and I have my input file right here as a .i. So I'm going to type in /combined OPT. In Linux, whenever you want to run, if you want to run any executable that's in the current directory where you're at, you have to do a / by convention. Now I'm going to do -i. The I flag indicates that whatever comes after it is going to be the input file. So the input file that I want to give Moose is Bridge Fletcher, and I press enter, and oh, interesting. Of type legacy. Okay. So that's an error. So I'm going to go ahead then. Oh, that's a deprecation warning. Kernel/tensor mechanics syntax is deprecated. So that just means that it's old. The input file has some old stuff in it that it doesn't like anymore. So I'm going to go ahead and CD and oh, here's the reason. Error, unable to open file bridge.e mesh. So in order to do this, let's go ahead and go back into nano Bridge Fletcher. The mesh here in Moose, it needs to know what the geometry is. So, it's told a few displacements, type, this is a file mesh, it needs to read in the file, and the file is bridge.e. Bridge.e, in this case, any file with a .e at the end means it's an Exodus file. That's a nice file format that Moose uses to write out results, and in this case, import geometry. So I'm going to come down, and you're going to notice here too, at the very end in the executioner, down here in the outputs, it's going to say Exodus equals true. When you're writing your own Moose files, you want to do that. So that's something to worry about. I just need to go CD back to projects, Moose, modules, solid mechanics, examples. I think it was a bridge. I'm going to CD back there. I'm going to show, and I see that I have my bridge.e right here. So let's go ahead and copy bridge.e. I'm going to copy that to my squiggle, project, my project. Now let's go ahead and CD. If you want a nice little shortcut, you can CD back to your hyphen. That just means you want to go back to whatever directory you were in previously. So I'm going to do that. That happens to be my project. Very convenient. ls. Now I should have everything that I need to run. So I'm going to do /combine-opt-i bridge_fletcher.i. Now it's going to tell me that's deprecated, but it's still going to run. It's going to tell me what my geometry is like, and it's going to start running here. And fortunately, it's a steady state, so it's not going to need to step through time, but it is 3D, so it's going to take a little bit to converge. You'll notice that in Moose, it'll go through some nonlinear iterations. So that's what these ones are. Boom. And then it'll tell you what the residual is, and for each of the linear iterations as well. And it got down to where the residual was low enough and converged. And it tells us the performance graph. If you guys have issues or really want to know or get into Moose, then that's that. You'll notice it took 30 seconds. So that wasn't too bad, but you can imagine that these things probably scale, especially if you want to do 3D. So something you can do is right in front of here, you can do MPI exec -n. Let's go ahead and say 4. And that will, if I remember right, this will execute the executable here using the number N4 here. N is how we indicate the number of processors we want to use. So we say we want to use 4 processors here for this file, and MPI exec will go ahead and do that for us. The advantage of using more processors is you can do it faster. So unless it's already going, boom, boom, and a boom. And you'll notice now that instead of taking 30 seconds to run, it took almost 15 seconds. So that's really nice. So if I ls now, I can see that I have this new file right here, bridge_fletcher_out.e. Now I want to examine what's in that executable file. I can't do that from WSL. So what I'm going to do is I'm going to copy bridge_fletcher_out.e. I'm going to copy that to my Windows. Now, in Linux, you have the very roots of Linux is always just the slash. So I'm going to change it to slash to the mount directory. In WSL, your Windows directories are mounted to mount. So now I can go ahead and see that I have C here. So I'm going to mount it to C. and I can find the equivalent here. If I come over here, Windows SSD, the C, I have drivers, inept pub, min-gw, perflogs, and all that. Let's see here. And I have my drivers, min-gw, curvery, perflogs, all that. So I want to go into users. Let's see, I want to do documents. What do I have in documents? Let's go ahead and do, let's do right here for now. So I'm going to copy my executable, my Exodus file over there. Now, if I look into my files and I look at documents, I have bridgefletcherout.e right there. That's perfect. So I have my file where I want it. In order to execute it, I'm now going to go out to the web. I'm going to search Paraview. Paraview's a wonderful, awesome system program that we can view results from simulations with. So I'm going to click download. I'm on Windows and I'm going to download this MSI executable. We're going to let it download. All right, that's completed. I'm going to open it up. It's going to say that it's an executable and needs permissions. I'm going to say that it's okay. I'm going to go through the wizard. I'll accept the terms of the license agreement. This is the default location. That's fine. It's in program files. And I'm going to stop.
For what?
Hey Alexa, stop. All right, so that's installing. I'm going to close this and this. It just had a little pop-up asking me if it was okay for it to make changes. I said yes. All right, so it's finished. I'm going to click finish on that. Now I'm going to open up Paraview. All right, I'm going to go ahead and close. I'm going to full screen this. I'm going to come up here to File, Open. And so now it's in Program Files in the bin. I don't want that. I want to go from the root up to users, flat, I want to go to Documents, and I want to select this file right here, my bridgefletcherout.e. Gonna click OK, and I'm gonna click Apply, and now we can see our nice little bridge here. All right, this is a cool little bridge. This is actually a lot cooler than I thought it would be. I thought it was just gonna be a boring little file. So we have our bridge here, and we can see what it is, and that's cool. So we're gonna come up here to this top bar. In ParaView, there's a lot of different bars. I'm just going to click right here. I want to see the displacements. And this is no displacement right here. I'm going to click forward. It's steady state. And it shows that it's all red because it's still using the same scaling. So I'm going to go ahead and scale. It says rescale to visible data range right here. So I'm going to click rescale to visible data range right here. And it's going to show me that, whoa, awesome. A lot of the displacements on this bridge are right where we expect, right at the top of the arch. So congratulations. In this tutorial, we learned how to download WSL by going into PowerShell and typing the command WSL-install. Once we did that, we came into WSL, we updated, we downloaded Conda, we made a Moose Conda environment, we cloned Moose, we compiled our executable, we ran our example problem, and we analyzed it in ParaView. Good luck with all your Moose work, and I hope this was helpful.